Okay, hello everyone. Thanks so much for joining for our last SAPHIR webinar of the year. I'm very happy to introduce today Michael Dozer. So he's a research physicist at CERN. He has expertise on antimatter experiments and quantum sensing, the topic of today's webinar. Also, he's an experienced science communicator, as I saw online. So we are really glad to have with us today. Michael, thank you for your time. Please go ahead.
My pleasure, and thank you for the opportunity. I don't think I've given a more distant seminar in my life, so this is really great. I'll be talking about quantum particle detectors, quantum sensors for particle physics, with the idea of trying to apply quantum sensors to both high energy particle physics and low energy particle physics. So the overview of the talk is very simple. I want to say a few words about what I mean with quantum sensors, and how these quantum sensors actually fit into the landscape in a lot wider sense, what quantum sensors are good for, before giving examples from quantum sensors as they're being applied for low energy particle physics here at CERN and in a somewhat larger context, as well as then giving you some ideas about how one might be able to use quantum sensors for high energy particle physics. So let me first say a few words about what I think a quantum sensor is. This is not the standard definition, but it's close to the standard definition. So the idea is that quantum sensors are able to register a change of quantum state caused by the interaction with an external system. And this can be a transition between a superconducting and a normal conducting state, or within an atom from one energy level to another, or within a resonant cavity from one resonant frequency to another resonant frequency in a quantized manner. These are highly sensitive and highly specific sensors for minute perturbations. And with this in mind, the definition I'm using was coined by Mariana Safronova. She defined it like this: a quantum sensor is a device, the measurement and sensing capabilities of which are enabled by our ability to manipulate and read out its quantum state. And I would add and or read out its quantum states, because you'll see later on that some of the devices, when one applies them to high energy physics, actually don't really allow manipulating the quantum state beforehand, but do allow reading out their quantum state. Now, obviously, the energies needed to induce these quantum state changes are very low, and so naturally, quantum sensors are ideally matched to low energy particle physics, but I'll talk about both. And what I will not talk about in this presentation is about entanglement. This is the heart of quantum sensors normally. And unfortunately, entanglement does not yet play a huge role, but you'll see that we're starting to look into whether we can actually implement it. Now, if I have a menu of quantum sensors, I'd like to sort of give you an overview of what is out there in terms of the physics that one can reach. And here, what I've shown is a list of possible quantum sensing technologies applied to the search for dark matter, where dark matter can be anywhere between ultralight dark matter, 10 to the minus 22 centimeters, electron volts, all the way up to ultra heavy dark matter, 10 to the 14 electron volts, or even more. And depending on the mass range that one is looking at, specific families of quantum sensors, spin-based sensors, exotic atoms, semiconductors, superconducting devices, nitrogen vacancy diamonds, engineered materials, or even optomechanical sensors will be most appropriate for a certain mass range or energy range or interaction range. And with this in mind, so this is really enormous numbers of technologies, we've been focusing on a smaller number of families of quantum sensors, of quantum technologies. And in fact, as part of the European Committee for Future Accelerators roadmap, we identified 6 families that we think are most appropriate for future developments. On one hand, superconducting devices, so transition edge sensors, nanowires, cryoelectronics, then spin-based or nitrogen vacancy diamonds, then optical clocks, then ionic atomic molecular systems, then optomechanical sensors, and finally a very large family of materials engineered at the atomic level and that are zero, one, or two-dimensional materials. And with these kinds of families of quantum technologies, one can address a wide range of physics topics, search for new physics beyond the standard model physics, searches for axions, axion-like particles, dark matter, or non-dark matter, ultralight particles. One can test quantum mechanics, the foundations of quantum mechanics, things like wave function collapse or the origin of decoherence. One can test fundamental symmetries, for example, through searches for electric dipole moments or breaking of fundamental symmetries, Lorentz invariance, CPT, CP violation. And of course, one can use these quantum technologies to develop new types of detectors. So to say a few words about what is happening in high-energy physics, or at CERN in particular, CERN has three areas which try to incorporate quantum technologies into the physics that we're doing. On one hand, CERN has a quantum technology initiative, and I'll say a few words about that. CERN also has a area where one tries to develop new types of experiments, some of which will rely on quantum technologies. And finally, CERN is involved and is the driver in some way of R&D on quantum sensors for particle physics. So let me first say something about the CERN Quantum Initiative, which is now in its second generation. This was the situation a few years ago, from 2020 to 2023, where we tried to identify in the four areas of quantum technologies, quantum computing and algorithms, quantum simulation and theory, quantum sensing, metrology and materials, and finally quantum communication, whether there are specific areas that are relevant to the kind of physics program that is carried out at CERN. I will mainly be focusing on this area here on quantum sensing, where we had for a few years budget for a few PhD students to work on quantum dots, on graphene, and on operating systems to assess whether these could be relevant for high-energy physics applications. Now, since the beginning of this year, CERN has gone into the second stage of the quantum initiative, which really focuses now on technology, on trying to build specific technologies that go beyond what is currently possible and that builds on CERN's expertise. And here, these are more interdisciplinary projects. For example, building exotic atoms for new types of qubits, trying to build tunable superconducting RF cavities for axion searches, but also for as another possible type of qubit. Uh, in fact, both of these are really multi-qubit demonstrator platforms. And then also to try to see whether some quantum technologies like superconducting devices could be relevant either for charged particle detection, for searches for milli-charged dark matter, or as high precision detectors for spectroscopy of exotic atoms. So these try to combine different areas between high energy physics and atomic physics that is carried out here at CERN. The physics beyond collider activity focuses much more on physics rather than the technologies. And here the idea is to see whether one can actually carry out a number of experiments using existing quantum technologies. And these really have to do with atom interferometry, the study of atoms, of particles, of ions, of nuclei, or the use of RF cavities for axion searches. And if I look at the roadmap itself, so these were the six families that I mentioned before. In a way, what we put into this roadmap is a vision for the next 20 years. Very ambitious visions going all the way up to building functional high-energy physics detectors with quantum devices based on quantum technologies, but also trying to see whether one can set up space-based sensor networks, whether one can detect relic neutrinos from the primordial production at the moment of the Big Bang, and try to see whether one can address foundational questions or investigate dark matter. And in a way, this roadmap explains or identifies the challenges that we need to overcome in order to address on a time scale of about 10 to 15 years from now, some of these very ambitious goals. And you can see that the bigger the dot, the redder the dot, the bigger the challenge will be in order to carry out the corresponding measurements. But what one also sees is that all these technologies that we identified are relevant in some way in achieving these goals. Now, having written that roadmap, we were asked to implement it, and this implementation has taken the form of a collaboration called Detector R&D 5, which is an R&D program on quantum sensors, where we've taken the roadmap topics, which are here in red, and well, found a different basis in which to look at them, which is much more appropriate to the way the communities work. And I'll come back to that here. We also have 6 work packages now focusing on specific families of quantum technologies, but I'll come back to these quantum technology families later on. So the important thing is that we have not lost any quantum technologies, but we have now tried to find a way in which we can most efficiently advance the R&D that is appropriate to a specific technology. So that's just the landscape in which all these activities take place. And now I'd like to talk a little bit about the types of experiments that are being done here at CERN or in areas related to CERN, and that cover some of these work packages. In particular, work package 1 is the study of particles, of atoms, of ions, of nuclei, of molecules, of molecular ions. And here the idea is really to test fundamental symmetries on one hand, but also to test our understanding of QED, of our best models of description of interactions, and to search for dark matter in certain contexts. So one of the workhorses that one can think of studying, working with most precisely, are highly charged ions in penning traps, where one traps a charged system inside a series of electrodes that create a vertical um, electric potential, and this whole thing is embedded in a magnetic field. So particles undergo a series of motions, magnetron, cyclotron, axial motions. And if one measures these frequencies, one can determine the parameters of these particles. Now, what is very interesting is to do this with atoms or ionic systems formed from atoms, because depending on the nuclear charge of these systems or the charge of the system, different systems like boron or argon 13 plus have exactly the same kind of level structure, like in a normal atom. But the interesting thing is that because of the very strong electric field, for example, in argon, where one has removed 13 electrons, which is this 13 plus charged, the binding energy of the levels scales as the square of the charge. The hyperfine splitting scales as the cube of the charge. QED effects, QED effects as the fourth power of the charge, but the sensitivity to external fields, to shock shifts, goes as the inverse sixth power of the charge. So these are systems that are very insensitive to perturbations, but at the same time very sensitive to beyond QED effects. And as an example, between boron and argon 13 plus, one can see that the level schemes are the same in both cases, but what is in the blue-violet region in the case of boron, the transition between the ground state and the first excited state here, of 250 nanometer, this is strongly shifted into the X-ray region, where this energy difference now becomes 19 nanometers. So very, very, very far in the ultraviolet. Whereas the hyperfine ground state splitting, which is normally in the microwave of 654 micrometers, suddenly shifts into the optical range of 441 nanometers, which means one can optically probe hyperfine splittings rather than carry out these measurements with microwaves. And that means one has an enormous increase in sensitivity and in precision in terms of tiny effects that go beyond the standard model. Now, one can do this in highly charged ions. One can do this also in molecular systems to look for electron EDMs. One can look for an isomer of thorium-229 as a nuclear clock, whose energy levels have just recently been measured here at CERN by Isolde, and one can look at clocks made of molecules or ions. And I'd like to give an example of an exotic atom that is a possible precursor to these highly charged ions that I just mentioned, and these are antiprotonic atoms. where one can exchange one of the electrons of a normal atom by an antiproton. This is a system that is not stable. The antiproton has no Pauli principle that will stop it from cascading down, ejecting all the electrons and then annihilating on the bare nucleus, removing a proton or a neutron. And this can then be dressed with an electron or an antiproton to form Rydberg highly charged ions whose spectroscopy, because of the very strong electric fields, is now, even in the Rydberg state, transitions in the optical range. And one can thus probe a hydrogen-like system very, very precisely in an area of a very, very strong electric field, both for standard model particles with an electron, but also for antiprotons and possibly also for muons at some point. And this same approach can also go further. One can think of building molecules in which one has incorporated an antiproton that would replace an electron either in the periphery, so at the outside. And this is very similar to the approach taken to search for an electron electric dipole moment in molecules. Or one can even build ab initio a molecule starting with this hydrogen-like highly charged ion of antiprotonic iodine, for example, or rubidium, and connect to that a very strongly negatively charged molecular cation, and then form a molecular ion where the electric field between the very highly charged nucleus on one hand and the strongly negatively charged molecule on the outside, on the other side, will produce a possible orientation axis, an orientation axis for a possible antiproton electric dipole moment. So this would be a way to carry out a CPT equivalent search for a proton electric dipole moment. In a completely different field, RF cavities, one can apply new technologies. So these examples of exotic antiprotonic atoms are being pursued here at CERN, as are these RF cavities, because a lot of expertise at CERN surrounding RF cavities is being developed, in particular in the direction of superconducting RF cavities. Now, if one uses RF cavities to look for axions, one typically has to take into account this factor of merit for the sensitivity for any axion, which is proportional to the coupling constant between an axion and two photons. So in these RF cavities, an axion couples to two photons, one of which is the magnetic field in which the cavity is embedded, and the other one which is then detected. Then the factor of merit is also proportional to the square of the axion mass, the fourth power of the magnetic field, the volume of the cavity squared, the inverse square of the temperature, and the quality factor of this cavity. Now, what this means is that if I want to maintain a figure of merit that is constant as the axion mass goes down to very low masses, I'm going to have to increase either the magnetic field or the volume. There's practically nothing else I can do, which means that there's only a certain area of axion masses for which these microwave cavities are particularly well suited. If I go to lower values, I have the problem that my cavity would have to increase quadratically if I go down by a certain factor. So if I go from microelectron volt axions to nanoelectron volt axions, I have a factor of 1,000 decrease in mass, which means I have to have a factor of 1,000 increase in volume. And this becomes unfeasible simply because one has to work at cryogenic temperatures. So the method that is used in a standard way is limited to a rather narrow range of axion masses. But if one goes to a new type of approach, which is called axion heterodyne detection, whereby one tries to have not one single resonant mode in a cavity, which couples to the photon that one wants to detect, but two modes. The idea here is to have a slight detuning between the two modes, where one of them is considered a pump mode, where one puts a lot of power into the cavity, and a second, slightly detuned mode is a signal mode, which is coupled to the pump mode by the axion mass. Now, having two resonant modes means I'm no longer looking for a coupling of the axion to the resonant mode itself, but actually to the difference between two resonant modes. So I can go to very small differences in frequency, which means I can go to lower axion masses. And if in addition I can even tune the splitting between these two modes, I can actually scan a certain window of masses. And that's the idea between this axion heterodyne detection, where one can then either mechanically deform the cavity to have two different modes in two different directions, or change the electric properties of this axion, of this resonant cavity, whereby again, through the change of the electric properties, one can change the tuning of the two modes and also their splitting. And if this works and one uses parameters that have already been achieved, for example, by the dark SRF collaboration in Fermilab, of 10 to the 10, then one can map out the mass region well below the standard resonant region, which is around here, around a micro electron volt, going from, say, nano electron volts all the way down to 10 to the minus 22 electron volts. And with some very optimistic assumptions, even reach the axion-like dark matter limit here. The third region of low energy particle physics that's being explored, or where CERN or activities at CERN can also play a role, has to do with atom interferometry, where currently one is trying to use standard 1 meter sized atom interferometers to look for axions, but also topological dark matter, ultralight dark matter, gravitational waves, and even tests of fundamental symmetries. So the idea here is to try to use these atom interferometers that have a scale of about 1 meter and scale them up to the level where 100 meter to 1,000 meter type atom interferometers become imaginable. So the idea here is being pursued by MAGIS at Fermilab, but also ION in the UK, MAIGA in France, ZIGA in China. And going from the current setup of 1 meter sized atom interferometers to the 100 meter scale means one needs to rely on vertical shafts, which have heights of somewhere between 10 and 1,000 meters. CERN's vertical shafts, access shafts to the LHC and possible future collider have a depth, a height of 100 meters or up to 500 meters. And given CERN's expertise in cryogenics, one should do these experiments at very low temperatures to get very good vacuum, but also coating techniques that are very common here at CERN, and especially the dealing with complexity and engineering, means that in addition to these activities here, which are taking place at the 10-meter scale, discussions have started to very seriously implement a 100-meter vertical interferometer at CERN in the coming years. This is a stepping stone to go to space. And to go to space, one needs both long-distance interferometers, but also very reliable technology, which is being tested by the Atomic Clock Ensemble in Space setup, which is set to fly in the coming years. These are Pathfinder technologies in a way. And the ultimate idea is to have a satellite mission in about 20 years' time with very long distance atom interferometers in space. And these are then the EDGE mission that is being worked on right now and where R&D is taking place. So these are the low energy particle physics applications of quantum sensors that I wanted to highlight. But I'd really like to also talk about possible future applications of quantum sensors to high energy physics. Now, this is a lot less obvious given that most high energy physics detectors rely on detecting not a single interaction, which is what quantum sensors are very appropriate for, but the product of many interactions between a particle and a detector. So here we have questions of ionization, scintillation, light, Cherenkov photons. These are all the results of many, many interactions. Nevertheless, we have come up in the last 2, 3 years with a handful of ideas that rely on quantum devices or inspired by them, and which are not necessarily used as quantum detectors per se, but whose properties enhance or allow measurements that are much more difficult to achieve otherwise. And of course, the focus here is going to be on the typical high-energy physics concerns of tracking, calorimetry, timing, possibly new observables, and pileup. And there's a big caveat. These are not established techniques. These are partly crazy ideas. Everything is very speculative. But you'll see that in some cases, some of these ideas are starting to show a real promise. So I'll be talking about four families of quantum sensors, quantum technologies, and trying to apply them to high-energy physics. These are metamaterials, so dots, linear detectors, planar detectors, nanolayers. Then atoms, molecules, and ions that are manipulated by lasers, typically, spin-based sensors, and superconducting sensors. And I'd like to start with the first one, these low-dimensional materials. And the lowest dimensional material is a quantum dot, where one can benefit from the fact that quantum dots have very good timing properties. Sub-nanosecond timing is possible with quantum dots. Here on the left-hand side, you see the rise and decay spectrum, the fluorescence spectrum of a cesium lead bromide nanocrystal deposited on glass. And one of the prominent components has a decay time of 43 picoseconds. So this is a very fast decay. And this is not just that particular material. This is a more general property of quantum dots. On the right-hand side, you see, for example, the decay time constant of sedeno gallium embedded in silicon dioxide, which has a decay constant of 210 picoseconds, or even more interestingly, cadmium selenide nanoplatelets, which have decay time constants of 24 picoseconds. So these are extremely fast scintillating materials. And that's one of the interesting properties of quantum nanodots. There's another interesting property of quantum nanodots, which is that their scintillation light, their fluorescence light, depends on the size of the quantum dot. On the right-hand side, you see the emission spectrum of quantum dots of different sizes between 2.3 and 5.5 nanometers. And you can see that the smaller quantum dots have an emission spectrum close to the blue, of ultraviolet, whereas the larger quantum dots of 5, 6 nanometers have emission spectra in the red, or if one goes to even larger quantum dots, into the infrared. So one has chromatic tunability, which means that if one uses them as a wavelength shifter, one can optimize the emission spectrum of the quantum dot such that one optimizes for the quantum efficiency of a detector. This can be a photodetector, but it can also be a very rapid detector like a silicon single photon avalanche detector. And if one deposits these on the surface of a high Z material of a scintillator, then one has a UV to visible light wavelength shifter. Of course, the idea is to embed these inside a scintillating crystal. And there, the question is whether one does this via polymer matrix, via epoxy matrix, or whether one embeds them really inside the crystal itself. And contrary to what my appreciation had been until about 2 weeks ago, I thought this would be impossible. It turns out that this is a standard technology. Quantum dots are already routinely embedded in silicon fibers. And so this is something that one could also carry on to, for example, lead tungstate crystals. But the really interesting thing is that the emission spectrum and the absorption spectrum can be fine-tuned not by the size of the quantum dot or their composition, but their geometry. If one uses triangular quantum dots, then the emission spectrum of those quantum dots can have a narrow band emission of the order of 20 nanometers, which means that the Stokes shift between the absorption and the emission is actually so large that the fluorescence light emitted by the quantum dots no longer gets absorbed by other quantum dots of the same type, which means that a device made up of these quantum dots will be transparent to any fluorescence light emitted by the quantum dots and a fortiori by other quantum dots emitting at even longer wavelengths. This is a very interesting and unique feature that really has to do with the modes, the quantum modes that are possible inside such geometries. And What this allows then is to contemplate something one could call chromatic calorimetry, where inside a calorimeter, one would seed individual slices of the calorimeter with quantum dots of different sizes. The first area being seeded with quantum dots that emit in the infrared, long wavelengths. This long wavelength light, for example, in this case at 598 nanometers, cannot be absorbed by the same type of quantum dots whose absorption spectrum ends at 582 nanometers, and a fortiori not by any of the other quantum dots further down in the calorimeter, whose absorption edge is even at lower energy, at higher energies at lower wavelengths. So light produced here will propagate through the whole calorimeter all the way to the end, and the same holds for all of the other slices. Any light produced in a slice will propagate to the end without being reabsorbed, which means that if one measures the spectral intensity at the end of the calorimeter, then when it has an image of the amount of energy deposited by an incoming particle in each of these different slices. So one can not only measure the amount of energy that a particle has deposited inside a calorimeter, but furthermore, one measures the shower profile of that particle. And this is really critical in differentiating different types of particles. Here's a simulation made by Yassin Haddad of how such calorimeters would behave if one deposits the quantum dots evenly within the different elements of the scintillator or as small slices between a segmented calorimeter. Remember, any red light produced here will go all the way through, the same here. Same is true for the yellow, the green, and the blue light. So if one measures the intensity of these different colors at the end of the calorimeter, one should be able to see where the shower was most pronounced. And this is a simulation of a 50 GeV electron that enters the calorimeter. Obviously, an electron will not fly very deep. It will deposit a lot of energy early on and will not make it very far into the calorimeter. So most of the light will be in the yellow and the red, and very little light in the blue and the ultraviolet. Of course, this is different if one increases the energy as the shower goes deeper. That ratio will change because now the electron shower will reach the more deeper parts of the calorimeter. And if one looks at the ratio of the red intensity versus the green intensity, so only two colors, so this versus this, then one can already see that measuring the ratio of these two allows one to measure chromatically the energy deposited by the electron. I don't need to measure the integral, I just need to measure the ratio of red to green. But one can do even better, and this is the result of a test measurement carried out by Devanshi Arora and for her as part of her PhD thesis, where this model that I present here, which is an abstract model, was implemented in the form of lead tungstate crystals separated by yellow emitting, blue emitting, and violet emitting scintillators. And again here, low energy electrons will deposit a lot of energy in this area here. So you expect to get lots of blue light and a little bit of yellow light, whereas high energy particles will have a shower that is deeper in the calorimeter. And so you expect an enhanced signal in the violet, a strong signal in the blue, and a signal in the yellow. And if one measures or if one compares, for example, the intensity of the blue of the purple light with respect to the intensity of the yellow light, which is shown here at the bottom for three different situations. First for electrons of 100 GeV, then for pions for 100 GeV, and then a comparison between the two. One can see that electrons deposit very much energy in comparable energy in the yellow and in the blue, whereas pions deposit less. And this allows one, just on the basis of the chromatic difference between the two, to do a 86% electron pion discrimination. So this is already something, it's not yet the nanodot device, but it certainly shows, or these two simulations and data show that these chromatic calorimetry approaches are actually quite interesting to pursue in the coming years. Now, these are just passive devices. Scintillating light is just produced without any major possibility to intervene. But there are, of course, also semiconducting quantum dots inside a active medium, gallium arsenide, indium arsenide mixes will create quantum dots or quantum wells with different scintillation properties. They're still rapid, decay times of the order of nanoseconds, but emission spectra in the infrared range, which is not an area that we are currently focused on, but that has a very interesting side property, which is that silicon is completely transparent at around 1400 to 1700 nanometers, which means that if instead of focusing on optical scintillation light, as we have done in the past, we were to focus on infrared scintillation, it might be possible to transport scintillation light produced on the inside of a high-energy physics detector towards the outside, and then detect that light in an area where one no longer has to worry about material budget. So this is something that is quite interesting to think about. Obviously, if these scintillators are far inside the apparatus, they have to be radiation resistant, and it turns out they are. Quantum dots are very radiation resistant, and that simply has to do with the fact that one doesn't actually perturb the crystal lattice and create traps for electrons the way semiconductors are normally normally suffer from radiation in their efficiency. In this case, even if there are displacements inside the quantum dot, this is not the property that one uses to obtain the fluorescence light. And one can go even further and try to think about active scintillators, where one would couple, for example, a silicon detector, where one produces many electron hole pairs with, for example, a quantum cascade laser, where each individual electron that enters the cascade laser, as it cascades down through the many energy levels of the cascade laser, so these are the many different layers through which the electron cascades, each one of these steps generates a photon, in this case, a terahertz photon, that is given by the energy, the electrically defined energy of the steps from the cascade. So what this would allow one to do is transform an electric signal here into a proportional signal of terahertz light, where the light intensity would correspond to the number of electrons that are produced by a DDX as a particle would go through a silicon detector, but is then multiplied by the number of steps of the cascade laser, which can be 50 to 100 times. And finally, one can work with two-dimensional materials. Here, the first attempts are really just first attempts, with the idea of, for example, trying to work in the amplification region of a TPC, where one produces many ion-electron pairs in the avalanche that one wants to use to detect the incoming electron from a TPC, but where the many ions then can drift back into the TPC itself and poison the TPC. If one can stop the ions from drifting back into the TPC region, one should be able to have a much cleaner situation. And one way to do that is to cover the region, the grid region between the detection volume and the amplification volume of a TPC with a monolayer of graphene, which will let electrons through. It's transparent up to 99% for electrons. Ions should be blocked and should not be able to go back into the drift region. Here, what one needs to do is find a way of creating monolayers of graphene that can span this opening pores of such a grid, and these are typically a micron or a few micron sized. So that's what I want to talk about, the metamaterials. And since I just talked about TPC, I'll just go right on to that area as well. Here you can see the amplification region of the TPC. This is what I was talking about in terms of the ions drifting into the main detection region here. In such a case where one has a TPC in a collider, particles are produced here, ionize the gas, and the electrons drift into this region here. Now, if we wanted to have a bigger signal in this area here, what one would need to do is find a way to enhance the amplification, the cascade itself. And one way to do that is by reducing the energy needed to release an electron from the atoms in this amplification region. And that is possible, or could be possible, if one were to laser excite the atoms in this region here into a highly excited state, where the ionization energy that is needed to release that electron is no longer from its deeply bound state, but from its highly excited state. So one only needs a little bit of excitation energy, a smaller electric field, to release an electron that is released by the interaction of the primary electron that is accelerated in the amplification region. This means one could work with lower electric fields, which means that any ions that are produced here might be kept from drifting back into the drift volume more easily. So this is one way in which one can think of improving a TPC. Another way to do that is in fact acting also in the primary drift region itself, where one excites the atoms prior to the collision of the two particles into a semi-excited state. Any pions or electrons or muons that are produced in the collision will then interact with these semi-excited states and again ionize them more easily. One can even take those atoms that have been excited but not ionized and then photoionize them in a subsequent step. So again, one can work with laser manipulation of the atoms inside the TPC to enhance the signal of electrons that are produced in this area here. This is very speculative because one isn't talking anymore about a handful of atoms. One's really talking about the full set of atoms inside a TPC. So one has to address 10 to the 30 atoms with lasers. This is quite challenging, and I don't know if this will work, but it's a possible idea to maybe work in smaller TPCs, maybe not yet for colliders, and see whether a proof of principle measurement could be possible. The third technology I'd like to discuss or encourage thinking about has to do with detection of helicity in charged particles. We currently have no way of measuring the helicity of a charged particle produced in a collider, except if that particle decays into multiple secondary particles, where one can then do a partial wave analysis of the secondaries in the rest frame of the decaying particle. But if the primary particle is, for example, an electron-positron pair from a Z0 decay, there's no way we can measure that helicity. Now, this is where this idea comes in, where one tries to carry out a helicity-dependent scattering by introducing a number of scattering planes inside a tracker, where two tracking planes define a direction. Then there's a scattering inside a polarized medium, which changes the direction, where one measures the direction again, another scatter, one again measures the direction, and the ensemble of the many scatterers themselves, as the particle goes through the tracker with these intercalated, very thin polarized planes, could allow one to measure the helicity, because the scattering probability is helicity polarization dependent. Now, one way to get a polarized plane in between tracking planes is to use nitrogen vacancy diamonds, which can be polarized through microwaves, and through their interaction with the neighboring atoms, polarize those as well. So one has a bulk polarization that is induced by microwaves and that can be measured with lasers. And the fact that the idea that this might work is borne out by the possibility of polarizing marker molecules, where marker molecules that are randomly oriented interact with polarized nitrogen vacancy diamonds at the surface and emerge as a spin polarized stream of marker molecules. Now, whether, again, this is feasible on a particle physics level has to be studied. First, ideas are being looked into with Géant 4 simulations. One has to have one scattering inside this material, but not multiple scatterings, so that one can really measure the change of direction induced by the spin-dependent or helicity-dependent scattering. And one needs to do this multiple times to build up a log likelihood probability for measuring the two spin states that the particle can have. And the last technology I'd like to quickly mention comes from superconducting devices. So these are single photon nanowire, superconducting nanowire single photon detectors, which work along the current principle. And one absorbs a single photon inside such a nanowire, that leads to local heating. And since there's a current flowing through this nanowire continuously, Because this area is normal conducting, the current is now forced into a smaller region, going beyond the critical current, which means it immediately blocks off the current, and that leads to a change in resistance or a change of the electrical properties of the circuit. And this change happens so long as that area is still warm. Of course, since one works in a cryogenic environment and has good thermal coupling, at some point this deposited heat will dissipate and one gets back to the original situation. So this leads to a voltage pulse that one can measure. These voltage pulses are very rapid. They have time constants of around a picosecond. And of course, this is not just going to produce, not just photons will produce these pulses, but also minimum ionizing particles that interact with the nanowires. The energy threshold for such a process is currently around 120 millielectron volt deposited inside the nanowire. And the goal is to improve this by a factor of 10 in the coming years for a relatively thick device of 100 micron. Now, if one compares the amount of energy deposited by a minimum ionizing particle inside 100 micron of silicon, that corresponds to about 20 keV, which means about 10 to the 6 times more energy than the sensitivity of the nanowire corresponds to. So nanowires such as these could be used to build a stack of trackers whereby in the beam dump experiment, muons could be detected in a muon detector and would lead to a signal inside these nanowires. So this is just a digital signal. It doesn't show you how much energy is deposited, it just is a 0 or 1. Muons will deposit energy and fire the nanowire stack of pixels, but would also be seen in an external muon detector, whereas millicharged particle, hypothetical millicharged particles, with charges down to a millionth of a minimum ionizing particle, would also fire this stack, but of course would not leave any signal in the muon detector surrounding such a device. This would, on one hand, detect a millicharged particle, but also would be a tracker for the millicharged particle because every single plane should fire so that one would be able to reconstruct the trajectory of these millicharged particles, these hypothetical particles, and reconstruct that they actually do come from the production target and are in time with that target. This timing information is also very important in another situation where one has collisions between many, many particles, for example, in an LHC colliding beam situation, where one would like to look for diffractive scattering. Now, in this mess of charged particles here, the two green tracks correspond to diffractive scattered protons. Now, the idea here would be to put these trackers, these very sensitive superconducting nanowire trackers, in Roman pots close to the beam axis and use the very high time resolution of around 1 picosecond to differentiate these green tracks from all the other tracks that come out of time. The time correlation between this green track and this green track would allow one to uniquely identify them. The nice thing about these nanowires is that one can also produce them at high TC, so a critical temperature of 25 Kelvin, if one uses high TC nanowires, superconductors and superconducting nanowires. So that's what these different detectors that we're talking about or thinking about correspond to. And I'd like to come back to the overall framework in which these studies can take place. So I mentioned the possibilities that these quantum sensors have for high energy physics, for low energy physics. Here are a few more details on the kinds of things one can do on a reasonably short time scale. And I hope I've convinced you that they're also possibly relevant for high energy physics. So the question is, what do we do next? Well, one of the things that is happening right now is the implementation of the ECFA roadmap, which leads to these kinds of pie in the sky ideas, and to actually build devices. And this implementation of the ECFA roadmap is in form of the detector R&D collaboration, where we had two goals: to prepare a proposal and to form a global collaboration. And global really means global. For me, it's the Americas, it's Asia, it's Europe, it's the whole world. We started at the beginning of 2023, had a first approach of different experts. had a workshop to discuss different ideas, which areas are the most promising, where are the biggest challenges, prepared a letter of interest, had an open workshop, a town hall meeting a few months later, where we went deeper into the different ideas and saw which ones resonated most widely. At the end of last year, we had a draft proposal that we then worked on improving in the first months of this year of 2024, and then submitted the proposal in May of last year and had a final presentation of the proposal by CERN's new committee, its detector R&D committee, who approved the DRD5 collaboration and its proposal at the beginning of June. And since then, we've been building up this collaboration that focuses on the 6 work packages, um, everything having to do with atomic physics, quantum systems, low-dimensional materials, superconducting detectors, spin detectors, entanglement. This is the only area where we have actually a work package trying to look into the feasibility of using entanglement, back action evasion, and squeezing in a detector that is relevant for particle physics. And then finally, also trying to look at capability-driven design, such as education, cross-disciplinary exchanges, test infrastructure. The structure of the collaboration is now in place. We have a collaboration board, we have a management board. We're in the process of identifying the work package leaders of the 6 work packages that we're looking into. And to give you an idea of the kinds of things that we think this collaboration should be doing in the area of atomic physics, for example, we have 3 sub-areas: exotic systems. This can be molecules, this can be ions, where we want to have a better experimental access, extended set of systems that we can play with, better theory, better calculations, and a measure of how sensitive to new physics specific systems are. So one can compare, for example, pionic atoms with exotic molecules. Then we have an area of atom interferometry, which is what I talked about in the ion setup on Earth and in space. And we have in that same group here also activities on distributing clocks and wavelengths. So the idea here is to have large-scale clock networks across the continent or even global through portable references and sources. And these are the kinds of things we want to focus on. The way we want to focus on them is by having people talk with each other, bringing experts together, encouraging workshops, publications, proto-collaborations, design studies, defining parameters. So this is not building anything. The individual participants build. The collaboration itself tries to bring different activities together in a coherent fashion to identify where we're missing something and to bring synergies together among the different groups. So we're really not building technical devices, we're building technical specs in some way. We're building a community that currently doesn't exist. There are many individual groups working in different areas, but a common focus on applying these technologies to particle physics doesn't yet exist, and this is the collaboration we're trying to make live. Right now, we have 100 groups involved from around the globe. You will see we do not have any groups from South America yet, very regrettably. I hope that we will get some groups interested also from South America. But from all other countries and areas, we already have a large number of groups that are interested in what we're doing and that are ramping up right now with the goal of benefiting quantum technologies and particle physics. And of course, this collaboration is open to all interested parties, and it's free to join. We have no membership fee, we have no annual fee, which also means we have no money, but that's a corollary that we're happy to live with. So that is what I wanted to tell you in this seminar, and I hope you have some questions.
Thank you, Michael. I find your talk very comprehensive and very detailed at the same time. I think this was great.
Yeah, I'm sorry I went through it very fast, so I hope you will have time to look at the recording. And if you want, I can send you the PDF so that you can go through it in more detail if you want.
Thank you so much. Questions, Francisca?
Hi, thank you very much for your very nice talk. Just wondering, in your opinion, from these different technologies, so metamaterials, atoms, and spin-based, where will you put your money on?
Well, there's two of them. The quantum dots, I think, is the best material right now. There we already have experimental outcomes. We know that this is going to work. Now it's a question of improving the calculations so that you get narrower band materials, emitters. But this is clearly going to work. I have no doubt about that. The superconducting wire, nanowires, transition edge sensors, kinetic inductance devices, magnetic microcalorimeters, there I would expect them to work. There are several groups that are starting to work on that. One in the United States, or several in the United States. One is collaborating with me at the University of Zurich to build these nanowires and then put them into beam tests. I expect this to work as well, but I'm not 100% certain that it will reach the sensitivity I'd like it to reach, in particular in the search for millicharge particles. I'm not sure that that is actually going to work. Now, the other ideas are much more speculative still. So we haven't done any tests, we haven't done any simulations. Only today I had a meeting with a group that wants to look into nitrogen vacancy diamonds. And there we just have to see what the parameters are, whether it even makes sense to go ahead. But the concept itself is too intriguing to just give it up like that, even if a simulation shows that that's not the right approach, because there are many ways to polarize materials. It doesn't just have to be nitrogen. It doesn't have to be vacancies in diamonds. It can be skyrmions in the semiconductor surface. It can be micromagnetic beads. There are many ways of trying to get local polarization, and one of these is bound to work. So in that order, I would say, and of course, my personal heart goes to the atoms, the atomic systems. Those are I love those.
Thank you very much.
Excellent. Mauro?
Okay, thank you very much, Michael. It was a really nice talk. So if I'm allowed, I have two questions, unrelated ones. The first one is if you could comment on, because you mentioned probing fundamental symmetries and in particular Lorentz symmetry. I am aware that at some point at CERN, they did something like probing well, not probing, but testing the universality of free fall with anti-hydrogen atoms, dropping them down and see.
Yeah.
So the first question is whether you can comment on that. And the second one is regarding this metamaterial spectrum. In particular, have you had any news whether the materials with topological phases have been considered for such ideas?
Okay, so first let me talk about the anti-hydrogen. This is a test of the weak equivalence principle for antimatter in a way. And if you drop antimatter and it falls the same way as normal matter, then you've tested the weak equivalence principle. There are three experiments here at CERN trying to test this. The alpha G experiment, who published the result that with a 30% uncertainty, G is the same for matter as for antimatter. There's a French experiment called G-bar, and there's my experiment called Aegis, who's also trying to do that. We're not able yet to measure gravity. We hope to be able to get there by the end of 2026. Now, the idea is, of course, first to measure the sign, which I think nobody has actually seriously considered to be different. But the real goal is to do precision measurements. And there, one will need at some point to go to atom interferometry to be able to get to the same kind of precision with antihydrogen atoms as one has with normal atoms. Precisions for normal matter are at the level of 10 to the minus 13, and we're barely scratching the 30% limit right now. So there's a lot of space still to go. Of course, one can also think about testing gravity, not just with antihydrogen, but with so antimatter or matter, but mixed matter systems, positronium or antiprotonic atoms, where one has a system that is metastable, which contains a little bit of antimatter, a lot of matter, or equal amounts of matter and antimatter. And this would allow one to test, in addition to gravity, also things like baryon number dependent interactions, lepton number dependent interactions. Fundamental symmetries like Lorentz symmetries through the spectroscopy of these hydrogen-like highly charged ion in the Rydberg states. One can also test QED, look for beyond standard model spectroscopically. So there's a wide range of possibilities in these exotic atoms that are only starting to be scratched. We've only begun making them, and there are many, many years still ahead of us in terms of that kind of physics. Now, the other question that you had is about topological materials. In principle, those are very promising materials. My problem is that I don't know enough about them. So I haven't read about them in sufficient depth to see where one could think of using them. But from the little I've read or little I've found out about them, they're very interesting. The fact that you can engineer the properties of some device that is at the scale of an interaction with a particle means that you can try to optimize that interaction in some way and get more information out than up to now. But I don't know enough to say something intelligent about it yet.
Thank you very much.
Thank you. Hero.
Okay, thank you, Michael, for the talk. Was very interesting overview of the possibilities for quantum sensors. I have a question regarding the spin-based sensors. If I understood correctly, you want to use MV centers just to polarize, or you also want to use them to detect?
Only to polarize. So in this case, really, the idea is to polarize these planes through the NV centers so that I have a very small, I mean, few hundred nanometer thick layer where I have a single interaction, a single scatter, not multiple scatters. And it's very hard to come up with low Z materials that are polarizable. NV centers are one possibility with carbon. I'm sure there are others, but these have quite some development behind them. And the fact that one can optically turn them on and off is something very encouraging for me. Now, we don't yet know whether that is actually feasible, whether the scatter of a charged particle, the helicity-dependent scatter of a charged particle, even if you have multiple scatterings in multiple polarized planes, is enough to differentiate between helicity forward and backward. That's a simulation will show that pretty soon. But up to now, we haven't had any manpower to look into this. So, in fact, many of these ideas are really at the level where they're just thrown out for people to try them out. And if they fail, then that's it. You have to come up with something different.
Mm-hmm. And regarding spin-based sensors in general, I know your talk is not about entanglement, but what about superposition?
Yes, so we have a few systems just today. That was why we were talking about these detectors. There's a group inside the CMS collaboration that wanted to look into top anti-top entangled final states, and to prepare a pure Bell state of top anti-top, and to see if one can detect their entanglement over a long distance. For that, they wanted to measure the polarization of the decay products. And that was sort of the background. Now, there are very few systems where entanglement like that is easily possible. One of them, and here, this is a paper I'm writing with with two theorists who came up with that suggestion, is to work with positronium, where you have electron-positron pairs that possibly we might be able to put into a Bell state and then propagate over time in an environment, test quantum mechanics with antimatter. So the top anti-top is to try to test quantum mechanics at very high energies and for very short times, because the state itself is barely a state. It's so short-lived. In the case of positronium, we're testing it with matter-antimatter systems.
I see. Okay, thank you.
Any more questions or comments? Well, if not, then we thank Michael again for your time. It was very interesting talk. Thank you, everybody.
Thank you. And I'll
Thank
send you
you.
the PDF, well, probably on Monday.
Yes.
If I don't
Yes,
send it, you
sure.
remind me, please.
Okay, I will. Thank you very much.
Okay.
Thanks, everybody.
Thank you,
Thank you
Michael.
all.
Ciao.
Bye.
Bye. Thank you all.